In section 3.1, we defined radian measure using the following formula. Arc length, S, divided by r, the radius, is equal to our angle measured in radians. If we take this equation or this formula and we multiply both sides by r, then we get the arc length formula. So S, the arc length, is equal to the radius times the angle, the central angle measured in radians. Because we actually took the formula for radian measure and solved it for the arc length S, it is important that when we use this formula, our angle must be in radians and not in degrees. For example 1, a circle that has a radius 25.6 centimeters, and we want to find the length of the arc that's intercepted by the given central angle. We want to round to the nearest 2 decimal places. So let's first draw a picture of our circle, and our central angle is 7 pi divided by 8. So we know that 8 pi over 8 would be right here, so 7 pi over 8, we'll say it's about right there. So here's our central angle, theta, 7 pi divided by 8, and the radius of our circle, we're told, is 25.60 centimeters. We are asked to find the length of the arc, so what we're looking for is the arc length on the circle that's measured off by that central angle. So our formula that we just talked about, the arc length is equal to the radius times the angle, the central angle, measured in radians. So our arc length will be 25.60 centimeters times our angle measured in radians. I recommend that when you type this into your calculator, that you type in first the numerator across the top. We're going to multiply top times the top and bottom times the bottom. So I recommend that you put 25.60 times 7 times pi, and then I recommend that you hit enter into your calculator. And then after you do that, then I'd recommend that you divide that entire answer by 8. If you put it all into your calculator at one time, it is important that you put the top in parentheses and then divide by 8. And when we round to the nearest 2 decimal places, I get that our arc length is 70.37 centimeters. So our arc length here, that length that was measured off by our central angle on our circle, 70.37 centimeters. Part B, we are told that using the same circle with the same radius, that our angle, our central angle, is measured in degrees is 210 degrees. So let's draw our angle. There we go. We want to know the arc length that's measured off by that angle, 210 degrees. So this is what we're looking for. Here, our angle is given to us in degrees, and in order for us to use the formula, it must be in radians. So let's remind ourselves what the conversion is. We do 210 degrees times pi divided by 180. And once again, when you put that into your calculator, I recommend that you do 210 times pi and then hit enter and then divide by 180, or put this into your calculator, 210 times pi, put parentheses around your numerator and then divide by 180. There's our angle in radians when we do that conversion. So we're going to get S is equal to our radius times our angle. So let's go ahead and put in our angle here. 210 times pi divided by 180. And I'm going to go ahead and just put that into my calculator all at once, so I don't have to do two calculations. I'm going to do all the way across the top. I'm going to multiply everything across the top first. So I'm going to put in 25.6 times 210 times pi. Then I'm going to divide all of that by 180. So I'm just going to do one calculation instead of doing two separate calculations. And when I put that into my calculator, my arc length turns out to be 93.83 centimeters. So we had to convert our angle first from degrees to radians, and I recommend holding off. We did the conversion, but hold off on actually putting it into your calculator until you actually multiply it by the radius as well. So we did the radius, top times the top, radius times that, put all that into your calculator, either hit enter, or like I said, put the parentheses around the top first and then divide by 180. Locations on the Earth are measured by latitudes and longitudes. And latitudes give the measure of a central angle. If we put the vertex at the center of the Earth and the equator represents our initial side, then that central angle is formed by going up from that. So this would be like 15 degrees on the Earth, and then going down from that. So this would be 15 degrees going down. We would say 15 degrees north and 15 degrees south. So if we treat the Earth as a perfect sphere and we work with these latitudes, then we can actually use our formula, treating that cross section of the Earth like a circle here. Since we're working with a circle and a central angle, and we know the approximate radius of the Earth, then we can actually use our formula, working with theta in radians instead of degrees, to actually calculate distances on the Earth given a particular cross section. So for example, Erie, Pennsylvania is approximately due north of Columbia, South Carolina. So what we're saying here is that we have a cross section of the Earth, and here we have our circle. That's our cross section of the Earth, and we're told that the radius of the Earth is approximately 6,400 kilometers. And we're told that Erie, Pennsylvania is located approximately due north of Columbia, South Carolina. It says the latitude of Erie is 42 degrees north, so using our equator here as our initial side, if I go up about 42 degrees, let's say that puts us right here. So here would be Erie, 42 degrees north, and Columbia is 34 degrees north, so the Columbia, South Carolina. So they're both going north in that northerly direction. What we're looking for then is the north-south distance between the two cities. So I want to know, what is this distance right here? So we're going to use our formula, S equals R times theta. We must make sure that we have theta in radians. So we're looking for the arc length here. We know the radius is 6,400 kilometers. Now we need to figure out what our angle theta will be. Well, the distance that we're actually working with here, the angle that we actually want to work with, is not going to be 42, and it's not going to be 34. It's going to be the difference, actually right here is what we want, this angle. So we want this central angle. So what we're going to have to do to find theta is we're going to have to first subtract 42 minus 34 to actually tell us what the angle measure in degrees would be between the two cities. And we get that that is 8 degrees. Well, we don't want 8 degrees. We don't want degrees. We want radian measure. So we're going to multiply by pi times 180 degrees. So we're going to convert to radians. So once again, as we use this right here as our angle theta, since we're going to convert that to radians, I am going to let my calculator do all the work for me. So I'm going to multiply 6,400 times 8 pi over 180. And I'm going to put all of that into my calculator at once. So it should look like this, top times the top. So we're going to multiply all three of these together on top, and then we're going to divide by 180. And once again, if you put it into your calculator all at once, then make sure that you have parentheses around the numerator, and then divide by 180. So the distance between the two cities, this is our arc length that we're going to solve for here. The distance between the two cities would be approximately 893 let's round to the nearest two decimal places, 0.61 kilometers. And it's an approximation, so we can say approximately, but this can work for any two cities that lay on the same north-south line. Here in example 3, we are working with two circular gears. And we can look at the picture and we can tell that we know the radius for each of these gears. The smaller gear has a radius of 2.5 centimeters, and the larger gear has a radius of 4.8 centimeters. We are told that the gears are adjusted so that the smaller gear drives the larger one. So the smaller gear would be attached to the motor and will actually move and will turn the larger gear with it. If the smaller gear rotates through an angle of 225 degrees, so let's go ahead and mark off what 225 degrees would look like. So it turns through a central angle of 225, and as it actually goes through that angle, there's actually an arc length that we can measure for that angle as well on the gear. So a point on the gear would move from here, let's say, all the way to here as we move or rotate through 225 degrees. We're going to call this arc length S. Now as the smaller gear moves, the larger gear also moves. It's being driven by the smaller gear. And actually, as it moves, the arc length that a point on this gear would move would be exactly the same as the arc length of the smaller gear. So these arc lengths that we're measuring off will be the same. So what we want to know is, what is this angle that the larger gear would move through in degrees? So let's find the arc length here of the smaller gear. So we have S is equal to R, which is 2.5 centimeters, times our angle, theta. Now for the smaller gear we have 225 degrees, and remember that we want to convert to radians, so I will multiply by pi times 180. And that's what I'm going to put into my formula. So we have our radius, and now we want theta, and we're going to go ahead and use the conversion here, 225 times pi divided by 180. Now we're going to put this into our calculator all at once, and once again we're going to multiply the top all the way across the top. I would recommend putting that in parentheses, and then divide by 180. So I get approximately, and I'm going to use as many decimal places here as I can. And I'm going to leave that into my calculator so that I get the most accurate answer possible. So I don't want to round until the very end. So this is all the information we have for our smaller gear. Now what about the larger gear? Well, now for the larger gear, we actually know that the arc length that is moved is 9.81747, etc. So let's go ahead and say that we know the arc length. We know the radius is 4.8. And now what we're looking for is our angle theta. And eventually we do want to get 2 degrees, but for now we're going to solve for our angle theta in radians. So we know that S is equal to r theta, and our S is already in our calculator. We're going to leave it in our calculators, saves time there, and we're going to solve our equation here for theta. So plugging in our information for S and for r, we're going to divide both sides of our equation by r. So that value that you left in your calculator, now we're going to divide that by 4.8. And that's going to tell us our angle theta. And when I get that into my calculator, I get about 2.0453077713. Now this is in radians. But when I look back up to what my question is asking me, let's go back up for a second. My question says, through how many degrees will the larger gear rotate? So I'm in radians right now, and I want to be in degrees. So let's convert our answer from radians to degrees. So what do I need to multiply by to get from this radian measure to degree measure? And once again, we're going to leave that in our calculator. We're not going to do any rounding until the very end. And I'm going to multiply this by 180 divided by pi. So we're just going to multiply the value that's already in our calculator, the 2.0 radians, and we're going to multiply that by 180, and then we're going to come in and divide by pi. And we're going to go ahead and round to the nearest whole degree. And I get 117 degrees when I round. So we want to make sure that we give our answer in the units that was requested. In example 4, we're going to look at a pulley that is raising a weight. Find the radius of the pulley if the rotation of 51.6 degrees raises the weight 11.4 centimeters. We're asked to round to the nearest tenth. So here we have our circle, our circular pulley, and we don't know the radius of it, but we do know that the rotation of our central angle would be 51.6 degrees. And we also know that as our pulley turns, that the weight is going to raise a certain amount. It's going to go up 11.4 centimeters. So basically, as it turns, the string or the cord will be laid onto the pulley. So what's really happening here is that as we move, the arc length that is moved, that pulls that pulley up, will be 11.4 centimeters. So we know two things. We know the arc length, S, is 11.4 centimeters. We also know that our angle theta is 51.6 degrees. We also want to convert that to radians, so we'll make sure that we multiply that by pi divided by 180. And what we're looking for then is the radius of the pulley. So let's plug our information into our formula. S equals r times theta. So our arc length, 11.4 centimeters, is equal to our radius, which we don't know, times our angle theta. And we're going to put this whole thing into our formula for theta. Make sure you do the conversion to radians. Now we need to solve for r, so we're going to multiply both sides by the reciprocal of this fraction. And when we do that, 180s cancel, 51.6 pi cancels, and we're left with r is equal to, and this now will be what we put into our calculator. We're asked to round to the nearest tenth, so make sure you do top times the top. So we're going to basically be multiplying 180 times 11.4, and I recommend that you put parentheses around the numerator, divided by, and now we're dividing by more than one thing, so we want to also put the bottom in parentheses as well. So what you should have in your calculator should look something like this. Parentheses 180 times 11.4, close parentheses, divided by 51, or sorry, we put parentheses around that as well, just to make sure that the calculator knows what we're dividing by. Parentheses 51.6 times pi, and then close parentheses. So you want to make sure you put parentheses around the entire numerator and the entire denominator so your calculator knows what you're dividing by and what you're actually dividing into. So now we're going to type that in our calculator and round to the nearest tenth, and I get a radius of approximately 12.7 centimeters. So what we see is that our arc length formula can actually be helpful in solving applications when it applies to a circular object and a central angle of rotation.